DSTC9 Check 2 Multi-Domain Task Completion 2 Overview. I'm Jinchao Li from Microsoft Research. I will give this talk together with my colleague Qi Zhu from Tsinghua University. So our track consists of two tasks. The first task, end-to-end task completion, is a continuation from last year. So the goal is to resolve the complexity of building dialogue systems in the multi-domain setting. The second one, cross-lingual dialogue state tracking, aims to address the problem of language portability between English and Chinese in the dialogue state tracking setting. So now I'm providing the overview of the first task, and Qi then will cover the second one. The history of building task-oriented dialogue systems has evolved with different stages. In the classical modular approach, there are 4 components: natural language understanding, dialogue state tracking, policy learning, and natural language generation. So the early dialogue systems are built with machine learning approach for NLU, with the rest parts use rules or templates. But rules and templates are not effective at solving off-track dialogues. They require tremendous human efforts and they are not scalable. So with this, there is a development of machine learning-based models, and we have witnessed the growth in the past decade. Especially in recent years, there have been growing research works focusing on building end-to-end dialogue system with only one model, especially with the benefits of pre-trained models. So these systems are generally compared with the same type as end-to-end compared with end-to-end, or like modular compared with modular. So there is a lack of understanding what the best system would be like if we assemble the SOTA module models and compare them into end-to-end setting. So in DSTC9, we host a challenge for the end-to-end task completion. The best performing team in automatic evaluation actually used the modular approach, and the best performing team in human evaluation used the end-to-end pre-training model. So as a direct extension of DSTC9, in DSTC9, we host another round of challenge to promote the technology of building end-to-end dialogue systems. The participants are expected to build a dialogue system that receives natural language as the input and responds natural language as the output. So there is no restrictions on the architectures that can be used in the competition. Participants can use pre-trained models and will leverage all the existing models or data sets in the community to improve their system performance. So the results, first the data sets. The dialogue systems will be evaluated in the Multiverse 2.1 as opposed to 2.0 at the DSTC9. So compared with the Multiverse 2.0 at DSTC9, 2.1 re-annotated dialogue states and utterance to fix the original noisy inputs, noise annotations. So based on Multiverse 2.1, we also augmented another version of Multiverse datasets in the repository. It fixes some label issues, including inconsistent spans, missing labels, and comma issues, and others. So to make the life easier for the participants, we also introduced a dialogue development platform called ComLab 2. So ComLab 2 is a successor of ComLab and incorporates some new features, including the SOTA models and tools for evaluation and diagnosis. So in terms of dialogue development, it provides the module models and the end-to-end models well integrated with Multiverse 2.1 datasets. So users can either apply the existing models or integrate their own models into a framework easily. In terms of dialogue evaluation, ComLab 2 provides user simulators and automatic and human evaluators. Both are also well integrated with Multiverse 2.1. So users can conveniently evaluate the dialogue systems offline using automatic evaluation or online with mechanical turkers. So in the automatic evaluation stage, the user simulator we use is agenda-based policy plus burst NLU plus template energy. Task success rate is used as a final metric for the ranking at the automatic evaluation stage. We also report some other metrics, including complete rate, book rate, precision, recall, F1 score for the slot detection, and also dialogue length. In the human evaluation stage, we host the submitted dialogue systems in the backend and allow MS mechanical turkers to communicate with the boss using natural language. So each turkers will be provided with a goal at the beginning of the conversation. For example, in the train domain, they will be provided with the day, the departure arrival city, and they have to figure out the actual departure time. So after communicating with the bots, the M-Turkers have to judge whether the dialogue is successful. They also need to provide the scores for natural understanding and response appropriateness on a 5-point Likert scale. If the dialogue is successful, they also need to provide the request slot values. So one thing I would like to mention here is like M-Turkers actually they don't have access to the backend system. So once they get the slot values, they have no idea whether the values is valid or not in the backend system. So we should call the success rate to judge as subjective success or success without DB grounding. So after obtaining all the slot values, we create the queries based on values and goals to query the database and to check whether there exists any entry in the database that satisfy all the constraints. So after this stage, we call this success rate as objective or success rate with DB grounding. So we take this average of these two as the final ranking metric. So here is a bunch of comparison between the evaluation and the DSTC8 and DSTC9. First, the evaluator. So the evaluator is pretty similar. There is only one change. The Milu NRU was replaced by Burst NRU. Then the goal sampling. The goal sampling is quite different. So here we first calculate the frequency of all the slot combinations in the multi-words data set, and then the sample the user goal based on slot combinations. So the values for each slot actually they are sampled from a database with additional mechanism enforced to guarantee that at least one entry in the database meets full constraints. So compared with DSTC8, the difference is the slot combinations are directly extracted from multi-words data set. So this change makes the domain slot distribution and simulated dialogues more consistent with the original data sets. So third, the number of dialogues. 500 for automatic evaluation at DSTC8. Now we increase this to 1,000. For human evaluation, at DSTC8, we run 100 conversations for each team. And if two teams have very similar results, we continue running the human evaluation until that the relative ranking of these two teams are stable. But now we increase the number of evaluation dialogues in human evaluation up to 500. Dialogue success evaluation is quite different, just as what I mentioned before. So for automatic evaluation, first, when we want to judge a dialogue is successful or not, one intermediate metric we use is the recall score, which only cares about whether all the requested slots are filled. Now we add a DB grounding constraints. So after collecting the value of all the requested slots in the conversation, it creates the query and to check whether there is any entry in the database. So we call this success with DB grounding. It's the same for automatic evaluation and human evaluation. The only difference is in human evaluation, we take the success rate without DB grounding plus success with DB grounding, take the average of them as a final ranking. The last thing, the baseline. So we've changed the baseline. The new baseline is using hierarchical hybrid code network, HCN. So where each HCN consists of an LSTM model. The full model is compressed of 76 HCM models. So where the higher layers are trained to identify domains and the lower layers are trained to identify the dialogue acts or select dialogue acts. So the selected dialogue acts are then backpropagated up to hierarchy and assembled at the top layer. So here is the submission results of DSTC9. Each team can submit up to 5 systems. As a result, we have received 34 submitted systems from 10 teams. So if we just look at the figures, out of 10 teams, 8 teams actually use transformer-based end-to-end model, and only 2 teams use modular approach. If we compare this to DSTC8, out of 11 teams, only 1 team uses transformer-based end-to-end models. So we can see a clear shift from modular approach to end-to-end approch. And if we also look at the 10 teams using modular approach at DSTC8, a lot of components actually use the rule-based models. So we can also see a clear trend of using rule-based approach to machine learning-based approach. Here is the evaluation results. So at the evaluation stage, we first set a threshold based on the success rate of the automatic evaluation. All the 34 models are sent for automatic evaluation, but based on the threshold, we sent 21 models for human evaluation. And this also includes the best performing models for each team at the automatic evaluation stage. So if we see these two teams, Team 1 and Team 2, Team 1 reaches the best performance of the success rates at the automatic evaluation stage, and also reach the best performing case in the human evaluation. Team 2, although it's ranked second in the automatic evaluation, but it reached the same success rate score at the human evaluation as Team 1. So both teams they actually use the end-to-end approach, with Team 1 use Plato 2 as the base model, and Team 1 use Plato 2 as the base model, and Team 2 use GPT-2 as the base model. So when we compare the automatic evaluation with the human evaluation, in general, they are consistent, but there are some exceptions. For example, Team 6 and Team 7, they are not very good in the human evaluation, but they reached the 3rd and 4th in human evaluation. So the one reason can be that in human evaluation we largely enforce the DB grounding, so they are not really doing well for the DB grounding. Also, the thing is in the report of Team 7, they briefly mentioned that there may be some issues integrating of ComLab 2 during the automatic evaluation. Besides that, it's still unclear why there is such a huge gap. And also, if we compare the best success rates at a human evaluation without DB grounding, it already reaches 82.6. If we compare this with the DSTC8, the best performing team reaches 68.3. So there is a huge gap. Although DSTC8 and DSTC9, the goal sampling approach is a little bit different, but this number already indicates that there is a rapid development of dialogue technology in the recent 1 year. So the last thing we can see from the human evaluation is success rates with DB grounding and success rates without DB grounding. There are a huge gap here. So we can see that the DB grounding is yet to be improved. Here is another dimension to look at the evaluation results. So at DSTC8, we can see that the 5th team on the left figure is the winning team in human evaluation, and it is the only team that uses a pre-trained model. When moving from automatic evaluation to human evaluation, it shows the least performance drop compared with other submissions. So this is a strong evidence that demonstrates the robustness of pre-trained model when facing the language variations in the human evaluation stage. In contrast, in DSTC9, when we largely enforce DB grounding criteria, we can observe a larger performance gap between automatic evaluation and human evaluation. So this indicates that there is still a lot of room to be improved for DB and knowledge grounding for pre-trained models. So in summary, from this task, we have learned several points. First, there is a clear system building trend from rule-based methods to machine learning-based methods, and also modular approach to pre-trained models. Second, database or knowledge-based grounding is yet to be improved. Third, there is still a gap between automatic evaluation and human evaluation. With DB grounding criteria, this gap becomes even larger. So building a robust model to handle language variations, typos are yet to be improved. We released an archive paper Colorado aiming to solve the problems about input variations in dialog systems. So please check this paper if you have any interest. Okay, this concludes the overview of the end-to-end task. So Qi, you can take over.
Okay, thanks, Jinchao. Thanks, Jinchao. Sorry, let me share the screen. Hello, everyone. I'm Ryuichi from Tsinghua University. Is there any sound problem?
I can hear you.
There is an echo coming, I think.
Okay.
Can everyone else mute themselves? Just the speaker can unmute. Okay. Yeah. You can continue, I think.
Okay. Can you
Yeah, it is better now. Yeah. Thanks.
Yeah. I'm Ryuichi from Tsinghua University. Next, I will give an overview of the cross-lingual dialog state tracking task. First, let me introduce the dialog state tracking task. Given the dialog history, the dialog state tracking modules predicts the dialog state that summarize the user goal or constraint up to the current term. Dialog state can be used to fetch relative information from a database, such as finding a hotel or restaurant that meets users' constraints. Thus, DST is one of the critical components in building a dialog system. Notice that in some cases, the system recommendation will also become a constraint if the user accepts this. With the rapid globalization process, the need for adapting dialog system in rich resource languages to low resource languages is increasing. To verify the language portability of existing monolingual DST modules and advance the cross-lingual technologies in building dialog system, we introduce the task of cross-lingual dialog state tracking in this track. In this task, our goal is to build a cross-lingual dialog state tracker for the target language using the resource in the source languages. We offer two subtasks. The first one is a cross-lingual transfer from English to Chinese using English multi-woods dataset. And the second one is the cross-lingual transfer from Chinese to English using Chinese cross-woods dataset. Besides the training data in the source languages, we also offer other resources. For both subtasks, we provide the training data in the source languages and the ontology mapping between the source and target languages, and the training data in target language, which is offered by the machine translator. The ontology contains all possible values for each source, which may not be handled very well by the machine translator in general domain. So we apply the human translations. To ensure the consistency of the translation of dialogues and the corresponding annotations, we replace the value that appear in the dialogue with their translation in the ontology first, and then translate the dialogue using Google Translate. We also provide 215 dialogues translated by machine translator and corrected by human as the development data. For testing, we collect 500 new dialogues for each subtask in the target languages. We first generate user goal in the natural languages using ConvLab 2 for both multi-woods and cross-woods. And then we collect 500 human-to-human dialogue in the source languages in a website. This website allow us to allow two workers to converse and make annotations online. During the conversations, both sides need to annotate the dialogue ad of their utterance, and the reader should also lock down the dialogue state that are used as query over the database. Then we translate the dialogue to target languages in a similar way as the development data, which use the machine translation and a human correction. We use half of the dialogue as the public test set and the other half as the private test set. And the final result will be the average of these two test sets. And here's the stat.
Is there any network issue?
Yeah, looks. It appears I can't hear too.
Let me pin Qiju. I will ask him to log out and re-log in and try if that works.
Hello?
Now works.
So in which page I'm done?
I think you can start from here.
Okay. And for both subtasks, we provide the training data in the source languages and the ontology mapping between the source languages and target languages. And we also provide the training data in the target languages by the machine translators. We first use the ontologies mapping to replace the value appear in the dialog, and then use the Google Translate to translate the dialog. This is important to ensure that the translation of the same value is consistent in different contexts. And we after that we apply the human human translation for the development data, which use the machine translator and then is corrected by the human. For each subtask, we collect 500 new dialogues for testing. We first generate new user goals using ConLab tool for both multi-woods and cross-woods. Then we collect 500 human-to-human dialogue in the source languages. We adapt the dialogue collection website of cross-woods, which allows two workers to converse and make annotations online. During the conversations, both sides need to annotate the dialogue at and dialogue state. The dialogue state is annotated by the wizard. We translate the dialogue to the target language in a similar way as the development data. And we use half the dialogues as public test set and the other half as the private test set. And the final result will be the average over these two test sets. We evaluate the performance of the dialogue state tracker using the following metrics. The first one, and is the most important one. We use the drawing goal accuracy to evaluate whether the predict dialogue state is exactly equal to the ground truth. And so accuracy evaluate the prediction for each individual slot. and average over all slots. Since the slot accuracies may be dominated by the situation that both prediction and labels are empty, we use slot precision recall and F1 to evaluate the prediction for no empty slot only, a micro average over all slots. We show that the difference between this metric and slot accuracy in this table. Each submission contains the prediction for the public test set and the model used to make prediction for the private test set. The results are averaged over the public and private test set, and the final ranking is solely based on the joint goal accuracy. For each subtask, one team is allowed to submit up to 5 models, and the best model is used for the final ranking. At the final submission stage, we have received 10 models for multi-woods transfer from English to Chinese and 8 models for crosswoods transfer from Chinese to English from the same 3 teams. The best model are all used translated training sets for training. Team 1 used the chain models for both multi-woods and crosswoods subtasks, which use a BERT to encode utterance. Inspired by some DST, they incorporate a 4-class state operation prediction task into the chain model. Besides the provided data translated by Google Translate, they use their own translation model to translate the data and use for training. For both subtasks, Team 2 was based on the best model of Team 2 was based on some DST, which generates the value directly. Since the generated value may have some discrepancy between with the ground truth labels, they use ontologies and some handcraft rules to post-process. Similar to Team 1, they use Baidu Translate to translate the original dataset into the target language and mix them with the original with provided translations as the training data. They have tried some cross-lingual pre-training models such as XLM and trained models on training data in both source languages and target languages simultaneously. However, the models did not benefit from the cross-lingual data according to the result of their experiments. Team 3 formulated the dialog state tracking as a sequence generation problem. The models take dialog history as input and output pairs of slot name and value. Their best model used multilingual BART, trained on the machine translation of the original dataset for both subtasks. They also tried GPT-2 and CWGPT for English and Chinese respectively, but got worse results than multilingual BART. Since multilingual BART can take data in multiple languages as input, they try to use the original dataset in the source language and further use the data from the other subtasks for training. However, both strategies gave worse results. We show the test data statistics and the evaluation results of multi-woods here. The new test dialogue are a little shorter than the original ones. Team 1 and 2 got similar results with 62% joint goal accuracies. Team 1 is slightly better than Team 2, and the other metrics are similar. As for the results on crosswoods, we have 2 leaderboards. During the evaluation, we found that the newly collected crossword data missed a number of labels for the name slot when the user accepts the system recommendations. Therefore, we utilize the database search results, which is selected by the system to compose the response, to correct empty labels using handcraft rules. This change is considered as applying 2 different evaluation approaches, and both the original and new leaderboards are valid. However, the new leaderboard is preferred. In the original leaderboards, Team 3 got the first place, while in the updated one, Team 2 got the first place. We also show the baseline results. We use some BT as the baseline, and is worse than the best performance for both leaderboard. Finally, let me make a summary. To our surprise, all the best models are trained on the monolingual machine-translated data instead of the both original data and the translations. Although translate then trends is strong setting in the cross-lingual transfer learning. Previous studies found that fine-tuning a multilingual pre-trained model on the original data and its translations in multiple languages together is more powerful. However, Team 2 and 3 got negative results when training XLM or multilingual BART on the Chinese and English datasets simultaneously. Team 3 also tried to use the training data of the other subtasks in both source language and target languages, but makes no improvement. The performance of the translate and trends partially depends on the machine translator, which may be the reason that Team 1 and 2 augmented the data using another translator to translate the original data set. Team 1 and 2 modified DST model that this model are the state-of-the-art on the English multi-use datasets, and they also got strong performance on Chinese multi-use datasets, verifying this model's language portability. And this is the overview of these tracks. If there are
any question from our audience?
Hi, I have a question.
Okay.
For the multilingual scenario, I just wondering because in the testing phase, you collect the data from the source language, but doing the translation to the target language as the testing data, right?
Yeah.
But why not directly collecting the target language data?
Sorry.
I just wondering whether you can directly collect data from target language.
May I request everyone else to mute when someone is speaking? Yeah. So, like, if someone is speaking, others can mute who are using speakers. Otherwise, it interferes with it creates an echo. Thank you.
Okay, so
sorry,
should I need to repeat it?
Yeah. Sorry.
But in the testing scenario, you originally collect the data for the source language and also doing the translation to the target language to do the testing, right?
Yeah. Yes.
But I think more intuitive, you can directly collect the data in target language instead of in source language and do the translation.
Yes, and we use this setting because we can the newly collected data may be more consistent with the original data sets in the data distributions for the user goal or some constraints. And we also consider to actually we also have the data in the source language and target language, so they may be used to make a they may be used to make a parallel data set to evaluate the performance for both source source language and target languages. So you can evaluate the performance of your multilingual dialog state trackers in both source language and target language using the same data sets.
I see. I understand. It will be more consistent if you use the translation using the source from the data in the source language. But I think in the practical scenario, probably you only have the data in source language, but you want to do the language transfer into the target language. So in the testing scenario, probably the data distribution will be a little bit different from the data you collected in the source language. So in this scenario, they will be more consistent, but probably it may not very suitable for the real data.
Yes, I know. I understand your consideration, and yes, that is the question. Maybe the new, maybe collect the data in the target language directly is more suitable for development new a dialogue system that can be transferred to the target languages. Yeah.
I see. So probably we can have like both sets. One is translated to the target language. Another one is the data directly collecting target language. And we can also compare the both.
Yes.
Okay, thank you.
I have a question. So like in some languages, actually, there are two ways of speaking. Like one is a formal way and another is an informal way. I don't know if this is true in Chinese or not, but like in such languages which have, or maybe even referring to a male and a female, they use different words. For example, English uses he and she. So in such languages, if we do vanilla translation of the entire dialogue, it may produce certain inconsistencies in the translation. Like, for example, the first utterance using formal language, whereas the second utterance using informal language. So are there like any did you do such analysis on the translated dialogues? Like if this is an existing problem of like the utterances not being coherent with each other when you do vanilla translation?
Yes, actually, the translation from English to Chinese is I think is it has less problems, but the translation from Chinese to English is may make some, because there's many name in the Chinese that hard to translate into the English, and there are some dish names in the Chinese and it's also hard to translate to the English, and that will cause the pre-trained model in the English hard to identify the meaning of this phrase or the words, that so it cannot make a recognition or make a matching between the dialogue and the new the translated name. So I think it's a part of the challenge in the cross-lingual transfer learning. Yes.
So even some proper nouns, as you mentioned, like they may be translated, whereas, so for example, my name Abhinav could be translated into its literal meaning rather than retaining the same name Abhinav in another language.
Yes,
right?
a name has less problems, but some entity names and entity is hard to translate, and in encoding of this entity in the target language may be also hard problems to express the meaning, same as the in the source languages. Yes.
Okay, I think we are now around 4 minutes behind. So let's keep, probably we can start with the next presentation. So the next presentation is efficient dialogue state tracking by mask hierarchical transformer. The presenter is Minlie. So Minlie, you can start.
Okay. Can you hear me?
Yeah, I can hear you.
Okay. Okay. Can you see the slider?
Yes.
Okay. Hello, welcome to my presentation. I'm glad you can join. My name is Minlie. I present the work we did here at Haipang Royal Fresh Information Network Company. The title is Efficient Dialogue State Tracking by Masked Hierarchical Transformer. Here is overview. Let me start by putting this work in perspective. The DSTC9 trick 2 has 2 subtasks. We attend the second subtask, and the goal of this subtask is to build a cross-lingual dialogue state tracker. This challenge includes two subtasks with different datasets, the multiverse 2.1 and the crosswords. The multiverse 2.1 has 7 distinct domains. On the other hand, crosswords is the first Chinese domain target altered dialogue dataset, which contains 5 distinct domains. This challenge translated test data of multiverse 2.1 in Chinese and crosswords in English, respectively. The dialogue state tracker will exact the slot value from each dialogue turn. The dialogue state at current turn must include all slot values appeared before. This slide shows the sample from multiverse in Chinese. And this slide shows the sample from crosswords in English. This table shows the difference between two datasets, and crosswords has bigger ontology than multiverse dataset. The performance of the dialogue state tracker will be evaluated by joint goal accuracy. This metric evaluates whether the predicted dialogue state is exactly equal to ground truth. Tracking the dialogue state is efficient for the system to pick its next action. The ontology usually contains slot name, slot value, and domain information. The pick list-based method needs to fix this ontology. Its performs well on small data sets, but not sustainable for real-world applications, since it requires complete ontology. Recently, the span-based method can directly extract the slot values from domain context, which not need to predict candidate slot value pair. But this method not shows the values which cannot be extractable from dialog, such as whether has Wi-Fi, which is a Boolean type slot. Open vocabulary-based method is the extended version of span-based method, which can handle the unextractable slot values. Meanwhile, it's not needed a predefined ontology, but transformer architecture such as BERT cannot be applied since the token length of dialog history usually more than 512, which is the length limitation of pre-trained transformer models. This table shows the result of each method on both datasets. We can see the performance of pick list-based method is more better than other two. Here we test the span-based method only on multiverse datasets, since the result cannot in line with expectations, and it's no need to test on the crossword dataset. We want to find the reason why pick list-based method has better performance. As shown in this slide, the same expression in the resource language will be expressed in different ways in pool resource language. Moreover, both span-based and open value-based results are mostly dependent on the expression, which is the red part of the utterance. On the other hand, the pick list-based results are more dependent on the slot value in its ontology, which is the blue part of the utterance. Furthermore, the span-based method cannot use fully historical dialogue information, and the open vocabulary-based method cannot use transformer architecture models since by 512 token length limitation. Finally, in this challenge, we use pick list-based method as our DST model. This slide shows how the masked transformer neural network merges the historical information, and the value of the negative infinity will be ignored after softmax layer. This slide shows that we can choose different masks for merge historical information before current tense. The first line are the masks chosen by local future encoder, and the second line is a mask used by global future encoder, which is same as a mask in the GPT-2. This is the encoder architecture of our model. First, we use two first models to encode the slot name and the turn level information respectively. The one with gray color is used to encode the slot name and slot value, which has the fixed parameters. On the other hand, the purple one is used to encode the turn information, which has trainable parameters. Then we use the multi-head attention to combine the future of slot name and turn level information after getting each slot word future. Slot word future is this. We use masked transform network to merge futures of turn summary as a global future. For local future encoder, we use the same method as above, but different mask transformer network to get the N historical futures before current tense. Finally, we use multi-head attention again to combine futures of slot name and contextual level for global and local encoder respectively. This slide shows the architecture of our model. We use joint learning to train both slot value predict task and the state operation predict task. Here, the state operation predict task is to predict the state of each slot, such as carry out, delete, update, don't care. This slide shows the data augmentation we use in this challenge. First, we use different translation models to translate the rich source language to the post-resource language. Secondly, we replace the slot value in the utterance by other slot values belong to the same slot name. We also found that there are some erroneous annotation in both multi-words and crossword datasets. For multi-words 2.1 dataset, we use the data of the multi-words 2.2 to fix the annotation error. In the crossword dataset, we found some slot values in the previous tense are disappeared in the current tense. We then add back those slot values to the DST. This slide shows the final result of our method on both datasets. Especially, our result is more stable on two leaderboards of crossword. Summary. First, we translated the training set of the rich resource language to the poor resource language and train the DST model within the same language. Secondly, we chose the pick list based model as our DST model, which can learn the contextual representation better than span-based and open vocabulary-based models. Thirdly, we do the data augmentation by using different translation models and slot value replacing trick. Finally, we fix the erroneous annotation by using multi-words 2.2 for multi-words 2.1 dataset and adding back the disappearing slot values for crossword datasets. Thank you.
Thank you for the great talk, Minlie. Is there any question?
Yes, I have a question. So you use the mask mechanism or the mask transformers to encode the local feature, right?
Yes. Yes.
but the transformer is designed to encode the bidirectional information. So the earlier utterance may also have the information from the later utterance. So by using the mask, by using the mask for the later histories.
Yes.
You will.
I see. This is a masked transformer. It's not a bidirectory. It's a single directory. You can see here. The negative infinity is ignored by the.
Yes, but it's still. How can this result of better representations? Since if you use the original one that has no mask for the later utterance, and it will also encode the full information, and probably the attention will be learned automatically, and you will not need to specific the mask for example for the 0 histories or 1 history or 2 histories. Will is there any ablation study for which one will performing better?
We use different history mask into our subtask state operation prediction. This part. We try different N history, and exactly we found that 1 history is the best result.
So it's most important is the last utterance, last turn.
Yes, we want to say that it is a general way to merge any part of the dialogue history, but in this case, only the last turn is the best result.
Oh, okay, thanks.
Is there any other questions? I also have a question. So you mentioned you use annotation corrected version for the final results, right? So is there any result that shows a difference between the different version of training data?
Sorry,
yeah,
I can't.
Oh yeah, my question is you fix the errors in the annotation. So use that data set for the final results, right? So is there any results for the original version of the multi-words? So we can see the performance gap between the error corrected version of data sets and the original version.
You means we change the annotation.
You fix the annotation. So is there any result that shows the performance before the annotation got fixed?
Before the annotation fixed, let me see. Sorry. Let me find the paper.
Okay.
Exactly. We in the experimentation we found that there are actually 2 or 3 point gap between the before before annotation and fixed error. 2 or 3 points gap. Can you hear me? I'm not writing.
I can hear you. I can hear you. So what kind of thanks for the number. So do you have still remember what kind of errors did you fix? Is it more like state errors or some other errors?
Yes. It is something that system say the hotel name, but system say the hotel name, but the annotation were not tagging this hotel name, and we add this system. The system gave the name to the train data.
So missing label. This is.
Yes, and another missing is about time. It says after 9 a.m. and usually it get 9:15. Then we fix to 9 a.m.
Okay, I see. It's more like format. Thank you. So, are there any questions? You can post your questions on the chat or just shout. No. Okay. Thank you again, Mingmao.
Thank you.
The next presentation, I think it should be started in 2 minutes. So if the presenter is already here, just be prepared. Oh, I say Jonáš and Vojtech. Since the 2 presenters are already here, I think we can start early. So the next presentation is AuGPT, dialogue with pre-trained language models and data augmentation. So 2 presenters are Jonáš and Vojtech. Pardon me if I don't pronounce your name correctly.
Yeah.
You can start.
You can call me Jonáš.
Yeah.
It's all right. Can you see my screen? No.
Yes.
Okay. Okay, so hello, my name is Jonáš Kulhánek. I'm from the Czech Technical University, and I'm here with Vojtech, who will be presenting with me jointly from the Charles University. And we'll be talking about our end-to-end dialogue system, which placed 3rd in the competition. So let me start by introduction. Our model is based on the Solist architecture. It means that we use an autoregressive language model to model both the Bailey state and the response. And we have 2-stage decoding. First, the Bailey state is decoded, and then the response is decoded by using the same autoregressive language model with the same parameters. And we use GPT-2 as our language model. Now I will explain the architecture in more detail. So first we start with the dialog context, which means the concatenation of past utterances. And we pass this string to our GPT-2 model. And GPT-2 model then generates the autoregressively generates the Bailey state. It generates it token by token. it means that we use a string representation of the belief state. And when training this, we use cross entropy, and when decoding in the inference time, we use greedy decoding to do that. Now, here in this box, you can see the string representation of our belief state. I will talk about it in more detail later. And we parse this, pass it to the database. Database returns the results, and we use these numbers, the counts, again as an input to the GPT. Now let me talk about the representation of the belief state. Here, the representation is a JSON-like structure where here is the domain and then the slots and values for each domain. And these slots do not correspond exactly to the multi, as you can see. He replaced the underscores and these tokens by spaces to make it seem more natural. Also, we keep a fixed order of the belief state items so that we can detect what we call active domain, which is the first one. And the active domain will be important later when we will talk about the lexicalizing the response of our system. Then here on the second line, you can see the representation of the database counts, which is used as an input to the language model to generate the response. Okay, so we are here. Now we concatenate the user, the Dialog context with the belief state and the database result count. We pass it to the GPT and generate the response. Now for training the language model, we use unlikelihood loss summed with the cross entropy loss. Unlikelihood loss basically penalizes the model when it uses the same tokens multiple times. So it helps with making the responses more diverse. And when decoding, when we infer, when we generate the response, we use nucleus sampling. And we generate the lexicalized response. And it means that we replace any concrete values like names of hotels and other values, etc., with some general tokens, like this one. This is the actual response generated by the model. And the important difference between the multi-was lexicalization and our own is that we drop the domain. Usually there is like a domain underscore the slot name, and we drop it and use only active domain. When we lexicalize back, we use active domain to determine which domain should be used in the response. Okay, so this is how we generate the belief state in the response. And we also use consistency detection auxiliary task, which means that we attach a binary classifier to the last hidden representation of the GPT model. And this task is used only during the training, and it helps the gradient. It helps it to guide it in the right direction. And in order to I will talk about this in a moment. So how we use this task, actually, we choose half of the batch to be correct, and we corrupt the second half of the batch to generate negative samples. And this is actually similar to Solist, and the difference is how we generate these negative samples. We choose one of the three changes with the same probability. Actually, we can choose like a multiple of them with the same probability. And one change is to randomly sample a belief state from the dataset. A second one is to randomly sample the database count from the dataset. And the third one, which is different from the soloist, is that we resample only the values corresponding to domain and slots. So the third one, we found it to be much more challenging, the previous one, because the model could easily learn what domain was mentioned in the context and decide based on that. So our new negative sampling strategy proved to be much more difficult for the model to learn, but in the results section you will see that it improved the overall performance. And we also tried other auxiliary tasks. We attached user intent and system action classifiers, but we didn't find them helpful for the overall performance, so we did not include them in the final model. Okay, so how our final model was trained. First, we've taken the taskmaster and scheme guided the datasets, concatenated them, and unified them in a way that we've joined their belief states to correspond together and to correspond to motivos, and train our model on these data to obtain a pre-trained model. Then we've taken the motivos dataset and we've generated what we call a clean sample subset of the dataset, which means that we've taken only these samples where the dialog was consistent with its goal. So it would actually have 100% success rate evaluated using motivos evaluation metrics. And these clean samples, then where we then paraphrases these clean samples using back translations, which means that we've translated them to several languages and translated it back to English to generate a much larger data set. And we've trained our pre-trained model on these data to get our final model. So how we generate the back translations. For that, we use our system, which we had already at our university, and it is based, or the architecture is similar to BART, and our model was trained on 40 languages, so we've chosen 10 which seem to work best and used them for generating the paraphrases. And the paraphrases were generally very noisy, but in our case, it didn't matter much because the overall performance increased nevertheless. The noise was actually helpful for the model to help it with overfitting on multivos dataset. Okay, so let me summarize it. We've applied data augmentation via back translation to get a much larger number of training samples. We've used a different strategy for a negative sampling strategy for the consistency auxiliary training task. We use different losses for the response and for the belief state, whereas for the response we use unlikelihood loss, for belief state we use cross entropy, and we also use different decoding strategies for the belief state, whereas for the response we use nucleus sampling, for the belief state we use greedy decoding, and we train only on what we call the clean samples.
For the results, so we evaluated our method in several ways. First, we wanted to compare to other similar end-to-end dialog systems that publish their results on the multiverse data. So we evaluated our system on the multiverse test set and computed inform, dialogue success, and blue score metrics. And according to the published results, we achieved state-of-the-art performance with respect to the inform and dialogue success metrics. However, our system didn't perform so well with respect to the blue score. The main evaluation, automatic evaluation method of the DSTC challenge was based on the Convlab 2 platform. In this evaluation scheme, we use a pre-trained user simulator that is trained on the multiverse data to mimic the user behavior. Then the evaluated system interacts with the simulator and several metrics are computed, such as the ratio of the complete dialogues, the dialogue success rate, the book rate, and also the NLU performance is evaluated with respect to the F1 score. So according to this evaluation, we also compared to some published results of other end-to-end dialogue systems, and at least at the time of the submission, we outperformed the other published end-to-end results. Additionally, we also performed an ablation study to confirm that our modifications that we introduce are really helpful for the system performance. So here, the most important metrics are the dialogue success rate, and our full model is in the top row. And we tried several variants of the model, each with some modification omitted. As we can see, almost all the modifications really help to improve the model performance, especially using the clean samples really improves the dialogue success rate. Also, our modification of the consistency auxiliary task help to improve the success rate a lot. Important thing here is that the Convlab 2 based evaluation is not deterministic. So in our experiments, the best model was the full variant of the system with all the modifications. But actually, when we submitted the model, the one that performed best was the one that didn't use the pre-training stage of our training pipeline. So this is the one marked with asterisks on our slide. So the best model from our ablation study wasn't the one that scored best in the challenge. Finally, the most important evaluation was the human evaluation that was conducted using the Amazon Mechanical Turk platform and human judges. So again, the main metric here was the dialogue success rate. And with respect to this metric, we placed third in the final evaluation. Actually, when no database grounding was included in the evaluation, so the provided information wasn't checked according to database, our model performed best. However, when database check was included, our model performance was much worse, and therefore in the final dialogue success metric, we scored for the third place. So we were also interested to get more details about our model behavior, and therefore we conducted more detailed error analysis. We followed multiverse tasks that were used to collect the original multiverse data and performed 130 interactive dialogues with our system. Out of these 130 dialogues, 50 of them contained some kind of error. However, some of these errors were still recoverable, so we encountered 17 dialogues that ended in the failure, which leaves us with 87% success rate, but here no database grounding was included in the process. Then we categorized the errors with respect to the source of the error, and we observed that the most common cause of the failure was bad information captured in the belief state or bad decision, basically bad policy decision of the model. By far, the most frequent errors were something we call hallucinated values. This is a situation in which the model uses a wrong slot value that wasn't that didn't occur in the dialog context and is not in the database. So we call it's hallucinated. It basically appears out of nowhere. We can show an example later. And other common type of error was due to lexicalization. As you already know, our model works with delexicalized utterances. Therefore, we need to perform lexicalization in order to generate the full and final system response. And this part is kind of tricky and is a source of a lot of errors. For example, it can happen that the model repeats the same value. It can ask, are you interested in a hotel or in a hotel? So repeated values and similar problems we encountered a lot. And there were other less frequent types of errors. For example, the system failed to capture a switch change of the domain. Here I can quickly show an example of such a failed or a dialog that contains errors. So at first, the user asks for information about a theater in Cambridge, and the system successfully provides the requested information. But then the user is interested in a place to stay, and the system fails to capture the change. So after 2 turns, the user explicitly states that the user is looking for a hotel, and and the model finally captures the information and informs about the hotel. However, here comes another type of error. So this dialog was full of errors, and here the model incorrectly talks about hotels in the north, while no mention of the north area was mentioned. So this is what we call hallucinated values. To conclude, we achieve competitive performance for end-to-end models on the multiverse data with respect to the inform and dialog success metrics. We also placed third in the dialog state tracking track 2 shared task, and we additionally performed detailed error analysis that gave us more insight into the model behavior. In the future, we want to use latent representations of the belief state, and also we would like to experiment with the lexicalization part and use a trainable model to do that. So that's all for us, and we published our code on our GitHub page. Now we are happy to answer your questions.
Thank you for the great talk. It's glad to see the high performance on the multiple data sets with corpus-based evaluation. So,
Yeah.
any questions?
Yes, I have a question. How do you do the pre-train on the taskmaster and schema-guided dataset? As far as I know, there's no belief state for the taskmaster.
Yeah. Okay. So for scheme guided, there is a belief state annotation, and for taskmaster, we generated belief state by aggregating the spans from previous utterances.
Yes, so it was basically rule-based, very simple rule-based approach when we took the language understanding information and just aggregated it over the turns to form a belief state in an artificial way.
Oh, I see.
So it was kind of heuristical approach, but yeah. Did it answer your question?
Did you predict the active domain for current turn? So
yes. Mm-hmm.
So all of your tasks are pre-trained on the taskmaster and schema, or just the belief state generation?
No, both the belief state generation and the response generation were pre-trained on the taskmaster and scheme guided. The whole model was pre-trained on these two. There was the same training pipe, or the training was the same for this model and this model, just the data were different. And here we used the initial weight from this pre-trained model.
Okay.
Yeah.
I have a question too about the fact that when you provide the output of the DB, the performance is not as good as the ones you don't provide this information. This was also shown in simple TOD, I feel, like if I remember correctly. And I think in the human evaluation issue, do you have any explanation why this happened? It's more related to the data, like is multi-was super noisy, or by the fact that the output of this DB are not real knowledge, but is simply the number of tuples that are in output, and this is not a strong enough signal for the model to interpret and generate a meaningful output. And the second question is about the generation of lexicalized answer instead of the lexicalized answer. If you had any preliminary experiment, and in that case, how could you compute the metric of success rate and inform rate?
Okay, to answer your first question, we had some insight. Basically, during the construction of the lexicalizer and the lexicalizer, there were some trade-offs which we've taken into account, and some of them were to incorporate the responses or incorporate the concrete values more into the model, like to delexicalize less or delexicalize more. And if you delexicalize less, then the responses seem more natural, but it is harder not to overfit on the multivos. So part of this was caused by this trade-off. I think this was the reason why we had higher score without DB and lower score with DB. To answer your second question, could you please repeat it again?
So yeah, about the lexicalized version. So in case you use fully lexicalized, so firstly, you need to return something from the DB. You cannot use like DB equal to 133 entities. You need to return something like a tuple from a DB.
Yeah.
If you use that and you generalize a lexicalized version of the output, so yeah, exactly. You don't have like DB train 1133. If you need to generate something lexicalized, once you generate something lexicalized, how would you think like you could compute the metric, or do you think like would solve the problem on the side of the fact that you have many error in the lexicalization? So in a sense, if you have a lot of output from the DB, would it be easier to generalize lexicalized compared to not having this setting and generalize a lexicalized version?
Okay, so the way how the lexicalization is done is that you have this the lexicalization, and then basically you take the records returned from the database ordered by something like usually you order them, or when there is an ability state, like sometimes then you order them to be the closest to the time which is in the ability state, and so on. And then you take these records and replace the tokens in the lexicalized response one by one. But the problem is when the response offers you a choice between one or more between more entities. Like for example, when the response wants to want to offer you 3 hotels, then in that case, actually it would work, because in our lexicalization we had a rule where we when one row of the DP was used, it was not used again when we use the same slot. But some I would say that most of the mistakes were caused by the choice of the lexicalization. When you replace all the names with the hotel, then you cannot do that. You cannot lexicalize back. And based on our experiments, it was like 80% chance that we would be able to recover the lexicalized data back into the response. So we've kind of expected it not to be perfect.
I see. Thank you.
If that answers your question.
Yeah. Thank you for the overview. Thank you.
Thank you. Thank you again, Jonáš and Vojtech. The next presentation is a hybrid task-oriented dialogue system with domain and task adaptive pre-training by Liang Zhang. I think this is pre-recorded video, so Abi.
Hi, I'm Liang from AAAI Lab. I'm happy to be here to present our recent work, a hybrid task-oriented dialogue system with domain and task adaptive pre-training. This is also a talk about our submission to DSTC9 multi-domain task-oriented dialogue challenge. This work is collaborative with another 6 researchers from AAAI Lab. First, please let me give a brief introduction about the shared task. In this challenge, participants will build end-to-end dialogue systems to assist humans to fulfill single or multiple tasks. For example, make a restaurant reservation, book a hotel, etc. The main dataset used in the challenge is MultiVoice 2.1, which is a large-scale human-human dialogue dataset. It covers multiple domains like restaurant, hospital, taxi, hotel, train, etc. But also, any external dialogue datasets are allowed in this competition. In the final evaluation, systems are evaluated by human users and a user simulator. Here is a little bit more about the evaluation metric. For human evaluation, the organizers recruit human users using crowdsourcing platform. Each user is provided with predefined task goals. For example, book a train ticket to Cambridge from Birmingham Newsgroup. The train should leave on Wednesday and arrive by 2045. The user then chats with the system, and after the conversation is finished, the user marks the task as a success or fail. The key metric of human evaluation is the success rate, which is the number of successful conversations over total conversations. The team ranking is based on human evaluation success rate. For the automatic evaluation, an artificial user simulator will chat with the system. There are some objective metrics from the user simulator, like success rate, book rate, inform rate, etc. You can find more details in the Conweb 2 GitHub webpage. This year, 10 teams participated in the challenge. We tied for first place in the human evaluation and ranked in second place in the automatic evaluation. Before talking about our method, I want to describe a little bit about the dataset. The MultiVoice dataset is a human-human dialogue dataset. For each data sample in the dataset, a user talks to an agent to fulfill a predefined goal. Here is an example of the dialogue and the annotation. And now we have a dialogue context. A user is chatting with the agent to book a train ticket. The user wants to take a train to go to Cambridge and then arrive by 2045. The train should depart from Birmingham New Street and leave on Wednesday. Before replying to the user, the agent analyzes the dialogue context and turns the user's request into a more structuralized object, the belief state. Then the agent looks up the database and locates the entry that meets the user's requirements. And then the agent decides how to reply to the user by creating a dialogue act. At last, the agent types a sentence in natural language and sends it to the user using the information above. So here, the annotation tracks the agent action and it can be used for training a dialogue system. So our goal in this challenge is to train such a dialogue system that takes in the dialogue context and reply to the user properly. Here is an overview of our end-to-end approach. We want to leverage pre-trained GPT-2 model and fine-tune it on the MultiVoice dataset and make it to be able to do end-to-end prediction. So first, we flatten dialogue context into a text string and then feed the string to the GPT model. We fine-tune GPT-2 to predict belief state and then let the system look for the corresponding entries in the database based on the belief state. At last, the system generates the final response based on all previous information. This fine-tuning strategy is not relatively novel, but many other work have used similar approaches before. But in our work, we do make some novel changes to the strategy, and it worked very well. And I will describe this in details in the next few slides. We want to first talk about the data delectionalization and cleaning. These two steps reduce data complexity and improve the model generalization ability. In data delexicalization, we use several heuristic rules to replace key entities in the utterances with placeholders, such as departure, time, restaurant name, etc. Most of them are the values of belief state and or the DB entities. Here are two examples. In the first example, Birmingham New Street is replaced by placeholder value departure. Leave time, arrival time, daytime are also delexicalized. And similarly, in the second example, hotel type and the price range are delexicalized. For data cleaning and normalization, we normalize time, abbreviations, and etc. Since we train models on delexicalized data, As a result, those responses predicted by the model also contain placeholders. So we need to recover the lexicalization in post-processing. We replace these placeholders with the real value from the dialog context or the entries from database. As we mentioned, we want to fine-tune GPT-2 on multi-voice dataset. Our recent work points out that before fine-tuning a language model, continue in pre-train it on domain-relevant text data can improve the fine-tuning performance. Therefore, we follow this idea to continue GPT-2 pre-training on dialog domain dataset before fine-tuning. There are two types of pre-training. One is domain-adaptive pre-training that pre-trains GPT-2 on external dialog-related datasets. And the other one is task-adaptive pre-training, where we pre-train GPT-2 just on the plain text of multi-voice dataset. And after doing this, we have a GPT-2 model that is tailored to the dialog domain. And in this page, I'll be describing how to fine-tune GPT-2 on the multi-voice dataset. We take the dialog context and the annotations of one turn and convert them into a long text string. The text string has 6 components. Dialog history, turn domain, which shows the domain of the current turn, and belief state, which is a flattened dictionary, and DB match, which indicates how many entities matched in the DB based on the belief state, and dialog response, and then the end of the sentence token. We feed this giant string to the GPT-2 model and carefully select the objectives that the GPT is fine-tuned on. For the final objective, we want the GPT-2 to predict turn domain, belief state prediction, and the response prediction. In addition, we have a contrastive objective where we create a negative sample and we give the label 0 or 1 to the EOS token to indicate whether the string is positive or negative. I will cover more details in the next slide. So the final objective is a combination of 4 objectives. Here, we describe how to compute the contrastive objective. In training machine learning models, introducing contrastive samples is a common practice. And we create negative samples by randomly choosing one of the following methods. We replace belief state with another random belief state. We replace dialog response with another random dialog response. Or we replace both belief state and dialog response with another random belief state and dialog response. So after creating the negative samples, we give the label 0 to the EOS token of the negative sample and 1 to the positive sample. And by doing this, we can consider a contrastive objective as a binary classification task on the EOS token. In addition to the neural model, we have 2 rule-based modules to correct errors and improve user experience. The first one is the fault tolerance module. Let's first look at 2 errors. In the first error, the user wants to make a restaurant reservation. In the predicted template, the system predicts the placeholder value day. But since the user hasn't provided this information yet, so it's impossible for the system to replace this placeholder with the correct value. And in the second example, the system repeats its response. What area of town would you like to stay in? So generally, this response is not something we want. And to fix this error, we let the system to generate a different response by adjusting decoding beam size or using different random seed. So after the fix, for the first example, the system replies, what type of food do you like? And in the second example, the system replies, I have 33 guest houses in the East. Do you have a price range? So both of these two responses are very good. The second rule-based module is what we call user interface. Here is an example. The user wants to book train ticket from Birmingham New Street to Cambridge. The system successfully books the tickets for the user, but it doesn't confirm with the user. So the user actually may not know train TR5933 is the right train, and the user may ask the system, does this train goes from Birmingham New Street to Cambridge? And this kind of true or false questions is something that the system may not be able to handle very well, and this could cause an error. This could cause an error response. So for such case, we modify the system response and add more information and manually add more information to it to convince the user that the train is the right train. After the fix, we provide all train ticket related information to the user, like departure, destination, leave time, price, etc. And this improves user experience. And besides this type of error, we made a few more rules for other error types as well in this user interface. And here are the evaluation results. Our success rate of human evaluation is 74.8%, and our language understanding score is 4.5 out of 5, and response appropriateness score is 4.4 out of 5. And these two scores are made by the human users. So I would say our system did a pretty good job on language understanding and the appropriateness of the response. And we did an application study on the domain and about the domain and the task adaptive training using automatic evaluation. And the result here shows that domain adaptive training improves the system by 3%, while the task adaptive training is not very effective. And we have made our code public. Please feel free to try our task-oriented chatbot. And thanks for watching. And if you have any questions or comments, just drop me an email or leave comment on the GitHub, or just ask me in the QA session in the workshop. Thank you very much.
I believe the author is present in the audience for taking questions.
Yeah, Liang is now here in the Zoom meeting.
Hi, this is Liang. Hi, can you hear me?
Yes.
Hi, it's the real Liang. Yeah, I'm happy to be here to take any questions.
Any questions? I have a question. So you just mentioned that the task adaptive pre-training actually is not effective. Do you have any idea why that's happening?
I think for task adaptive pre-training, we only pre-train the model on, or just pre-train the GPT-2 model on the plain text of multi-was dataset itself. So it might be the multi-was dataset is not big enough for the GPT to learn new things. That's our impression.
How many epochs did you use for the task adaptive pre-training?
I'm sorry, can you ask again?
How many epochs did you use for the pre-training?
It's similar to we fine-tune the multi-was about 2 epochs. Okay. And we set the learning rate to be very small.
I see. Thanks.
Yeah, I think there is an audience.
Yeah, there is audience questions. So the question is from Huang. So the question is, do you have any evaluation study on the hard-coded rules that you introduced for tickets?
No, we don't have a evaluation study for that.
Any more questions? In the paper, actually, you mentioned you have any plans on the improvements on DB grounding, right? Do you have any ideas so far?
Right. I think because when we're developing the system, we didn't consider DB grounding as a goal to optimize our system because based on last year's evaluation metric, this is not something that is considered. But I think it is important to include DB grounding because that makes the agent response more accurate to the user. I think to improve that, we were discussing about maybe we introducing more information from the DB to the model. Because right now we only the only access that we have to DB is to look up the DB entities based on the belief state, but we hasn't utilized any information from the DB. So I think that might be a promising way to go to improve the grounding, DB grounding.
Yeah, agree. And also in the soloist, one information we use for based on DB is the number of records based on the constraints. So this information still may not be enough for grounding issues, right? So hopefully we can learn more about how to make the DB information applicable to improve the model performance. Okay.
Right. Yeah.
So any other questions, you can just shout or copy paste in the chat. No?
Okay, thanks.
Okay, thank you, Baolin. I think now we can take a break, then 2 minutes break. After that, there will be an invited talk. Thank you again for coming to the DSTC9 Track 2 overview. Thank you.